Hi everyone, welcome to another video by Cheenta. I am Rajdeep, and today is going to be the new installment of the number theory series that I've been conducting for a while. In today's class, we'll look at a couple of things, starting from the thing that I ended on last time, which was looking at consecutive powers of numbers modulo a certain number. And really what we're trying to do is develop a theory of multiplicativity and multiplication modulo in modular arithmetic. We'll start with cancellation rule, and we'll look at Fermat's theorem and Euler's theorem, which are big and famous results in elementary number theory. And we'll use these ideas to solve a problem from the 1989 AIME. So I hope you enjoy that, and let's get into it. So as you can see, this is problem 9 from the 1989 AIME, right? Let's see what the problem says. It says that one of Euler's conjectures was disproved in the 1960s by 3 American mathematicians, and they showed that there was a positive integer such that 133 to the 5 plus 110 to the 5 plus 84 to the 5 plus 27 to the 5 is equal to n to the 5. Find the value of n, right? So this problem is actually really nice because it'll also show how to generally analyze situations like these. It's a good example of using modular arithmetic. And it's even going to be a precursor for the Chinese remainder theorem, which is a topic we'll cover soon. But instead of trying this problem right away, which at this point, feel free to pause the video and try it on your own, what I want to do first is look at the cancellation rule. Up until this point in the discussion of modular arithmetic, we've only really spoken about addition, subtraction, and multiplication. That they work the way they're supposed to when you go modulo a number, right? The obvious question is, can you divide as well? So in particular, if I had AB congruent to AC mod m, can I cancel the A from both sides? The answer turns out to be yes-ish. So the actual result that is true if AB is congruent to AC mod m, where ABC are integers, m is an integer, is that if AB is congruent to AC mod m, then B is congruent to C mod m divided by GCD of A and m, which actually makes a lot of sense when you think about it. So you have m divides A into B minus C, right? That's what this is equivalent to. You want to say something like m divides B minus C. So what this statement is saying is that once you kill the common factor of A and m, what's remaining is obviously going to be divisible by is obviously going to divide B minus C, which is what this is. Take away the factor of A, and that sits inside m, and whatever's remaining is going to divide B minus C. That's just common sense. And this may be a good exercise too for you to do on your own at this point. I won't get into it right now. But a perk of this is that if the GCD of AM is equal to 1, if A and M are coprime, then in fact, then AB congruent to AC mod M implies B congruent to C mod M. So you can cancel when you're cancelling by something that's coprime. This is a part of a general trend that you can kind of do division, peek into the general trend that you can divide modulo m whenever you have coprimality. That's the idea. The The point that here is, so I'll introduce the notion of reduced residue systems. It's a fancy word for a simple idea. What are the numbers modulo M? What are the distinct remainders modulo M? There are 0, 1, 2, all the way up to n minus 1. This is a class of residues. You could choose another class, but this is a full set of residues. Right? That's where the word residue comes from. Same thing as remainder. The point is that from here, choose all the numbers co-prime to n. And what's remaining is called a reduced residue system. What is the advantage of looking at this restricted set of system? A restricted set of numbers is that thanks to cancellation, these guys behave in a very nice multiplicative way. So in particular, if I look at the set S as the set of, numbers mod M, residues, if I just call A the set of reduced residues, with the GCD of A minus 1, then S is closed under multiplication. What does that mean? That if you take a number from S and you take another number from S and you multiply them, it will still be inside S. Which makes sense, right? If you take one number which is co-prime to M, take another number which is co-prime to M, shares no factors with M, you multiply them, obviously you won't magically get another factor, right? So S is special, and in some ways it's kind of the largest set you can get. That is not all the residues where you are closed under multiplication. It holds the multiplicative data of modulo M. Even better, you can divide here. So I'll give you an example of this, and this is where we'll get Euler's theorem. Yeah. I'm not saying that this is a proof of Euler's theorem, neither am I promising anything. I'm just saying that this is how we get Euler's theorem. It's a very natural result that will pop out of this. So you have S, right? S has some numbers, A1, A2, AK. Where what is K? K is the number of number of say I between 0 and m minus 1, both included, which are co-prime to M. For those of you, you might have made a connection by now. For those of you who already know this result, this number, so the number of numbers starting from the number of numbers from 1 to m minus 1 instead of 0. So it's only a slight technicality. It's really nothing to worry about. And also, obviously, 0 is not in this set. So we're just counting the number of elements here. Obviously, 0 is not here. A number is 0 mod m if it's divisible by m. So obviously, it's not going to be co-prime to it. So we're fine anyway. But yeah, it's a number of numbers from 1 to m minus 1 which are co-prime to m. There's a nice, neat way we write it, and that is phi of m, known as Euler's torsion function. It is simply the size of this set. This is the size of a reduced residue system. That's where it comes from. Okay, so what? The point is that I can choose some A in S. Okay, I can look at the set AS, which is nothing but just multiply every element in this set A with A. Right? Choose some element from the set S and multiply everything in the set S with it. So really what we're looking at is AA1, AA2, AAK. The cool thing is, because this set is closed onto multiplication, at the very least I can say that AS is a subset of S. This is just a symbol which means subset of. It's possible on the outset that maybe two numbers, there's the AAI is equal to AAJ. We'll come to that later. But at the very least, I know that all of these numbers are still going to be inside S because of this, right? Because S is closed under multiplication. But in particular, this implies that AI is equal to A. Why? Because note that all of this is happening mod M. Obviously, right? All of this is obviously happening mod M. You reduce mod M. Why is this true? Because A is co-prime to, since A was in S, it's co-prime to M, and hence I can cancel the A off. So in particular, all that has happened when you multiplied every element in the set with A is it just permuted the terms around. That's all that happened. You can take an example. Look at all the numbers mod 5. So look at all the numbers in the reduced residue system. 5 is a prime, which is why you just get all the non-zero terms. 1, 2, 3, 4. Choose some number 2. Right? And then look at, so this is S. 1, 2, 4. Look at 2S. What is 2S? 1 times 2 is 2. 2 times 2 is 4. 3 times 2 is 6, which is 1 mod 5, right? 4 times 2 is 8, which is 3 mod 5. It just rotated. It just permuted itself. This is the general trend. Okay? This simply follows because of the properties of the set S. Very natural thing. But I can levy this. In particular, as sets, AS is equal to S. The sets are the same. Right? 2, 4, 1, 3 is the same set as 1, 2, 3, 4. Obviously not in the same order, but sets are inherently unordered. We don't care about the order in which we write a set. When we do care about the order, we'll write it as a tuple, but a set is inherently unordered. We only care about what's in there. So what is in AS and what is in S, same thing. Particular, and obviously this is mod n. Everything's happening mod n. And what can I do? Multiply everything. So S was A1, A2, AK. Well, in particular, K is equal to Phi. Remember that? Phi is just the definition. So it's Phi by definition. That's what Phi is. And AS was AA1, AA2, all the way up to AAK. What can I do? Multiply everything in it. And the product will be the same because it's the same set. Particular, multiply everything. So what I get? A1, A2, AK is going to be congruent to A times A1 times A times A2 all the way up to A times AK mod M. Which is what? It's just A times itself, Phi m times, right? Called K times A1, A2 up to AK mod M. A1, A2 up to AK mod M. But remember, all of these numbers are in S, so I can cancel them out by the cancellation rule. What does this tell me? It tells me that A to the Cm is congruent to 1 mod M, which is nothing but Euler's theorem. So you can take a second to pause and understand what just happened, right? You can go back in the video and really figure out what's going on. Why did I ask you to look at that sequence? 1, 3, 3 square and so on, mod 10. Because the idea is that if you start inside the set S and you look at the powers of a number, you're going to stay inside S, right? Start with A inside S. Because it's closed under multiplication, A times A is also going to be inside the set S, and so on. And the idea is that in some sense, once you look at the sequence, so let's see what happens. 1, 3, 3 square is 9, 3 cube is 27, right? Which is 7, mod 10. And what is 3 to the 4? It's 81, which is 1 mod 10 again. So it's cycled through a bunch of elements. And in particular, Phi m, we'll see how to calculate Phi m in general, but Phi 10 is equal to 4. You can check this manually. So in a way, what this is saying is that since S is the size of the set S, when you look at the powers of a number, you're kind of going to be cycling through the entire set. Not really. Obviously, you will miss some elements sometimes, and when you don't, it's a special thing. But the idea is that if you keep looking at powers, you will, by the time you're done looking at all the possible powers, in that there's phi elements in the set, so you at most have to go to the phi power before you come back, right? So maybe take a second to ponder on that as well. It's a very interesting idea. But yes, that's Euler's theorem. And a special case of this is called Fermat's little theorem. This is simply the case that happens when you take M to be a prime. In that case, phi of P, right? Phi of a prime P is P minus 1. How many numbers from 1 to P minus 1 are divisible, are co-prime to P? All of them. And there's P minus 1 of them. Right? In particular, this tells me that A to the P minus 1 is congruent to 1 mod P for all A between 1 and P minus 1. Obviously, it's not true for 0. Right? If you raise 0 to any power, it's going to be 0. But another alternative way of writing this is that, which is true for all elements mod P, is this. Right? This, I can just multiply with A on both sides, and I'll get this. But this is true for all A mod P. Rather, all A in general, any integer. Right? So, this or this is known as Fermat's little theorem. Alright? Now let's go back to the problem we were looking at. You want to find an n which has this property. Immediately, one thing that you would want to do maybe is, if you were thinking of Fermat's little theorem, you have fifth power here, right? So if I look at any number mod 5, in particular what happens mod 5 is, n to the 5 is congruent to n mod 5 by Fermat's little theorem. So if I look at this, remember what I said about why we care about modular arithmetic? Is because if sometimes you want to solve an equation over the integers, when you go modulo a number, you're looking at only part of the picture, right? Because going modulo kind of deletes some data. So you make a trade essentially. You look at a smaller part of the problem, but in losing the detail, you also lose the obscurity. You're looking at a clearer but smaller part of the problem. So you trade off completeness for simplicity. So all that is saying is that if I look at this thing, mod 5, I will know what n is mod 5, right? Because this, when I look at this equation mod 5, I get all of these numbers. So for any number, n to the 5 is congruent to n mod 5, right? By Fermat's little theorem. So 133 to the 5 is congruent to 133 mod 5, which is just 3 mod 5, right? 110 is divisible by 5, it's 0. 84 is 4 mod 5. So 84 to the 5 is congruent to 84 is congruent to 4 mod 5. I'm just repeatedly using this equation, which is just Fermat's theorem. Plus 2, right? 27 to the 5, right? 27 to the 5 is congruent to 27 mod 5, it's congruent to 2 mod 5. Is congruent to what? N mod 5, right? Why? Because n to the 5 is congruent to n mod 5. This tells me that n is congruent to plus 1, 4 mod 5. So we have a piece of data about n. We started with nothing at all, right? And now we know something about n. It's a very specific thing. That n is congruent to 4 mod 5. This is actually enough, but I will still proceed with it. You can also look at this, equation modulo 3 or 2, and you would actually get that n is divisible by 3, right? Because this side, if you just, it's not very hard. We look at this thing mod 3, it's going to be 0 mod 3. And similarly, it's going to be 0 mod 2. That's actually quite easy. So we just saw what n is congruent to 4 mod 5, right? You can also look at this equation modulo 2 or 3, right? Looking modulo 2 is just asking whether n is odd or even. We just need to see if this is odd or even, right? 133 to the 5 is obviously odd. Odd into odd is odd and so on. This is odd. This is even, this is even, this is odd. Even plus even is even, odd plus odd is even. So the left hand side is even, as the right hand side is even. If n to the 5 is even, obviously n is even, right? So n is congruent to 0 mod 2. And you can do a similar analysis and see that this side is also divisible by 3. Not very hard, but I won't get into it. So in particular, if 2 divides n and 3 divides n, that implies 6 divides n, right? Think of it in terms of prime factorizations. If 2 is inside n in the prime factorization and 3 is there, 6 is going to be there. So n is congruent to 0 mod 6. N is congruent to 0 mod 6 and n is congruent to 4 mod 5. What I'm going to show you is actually the beginnings of the Chinese remainder theorem. The Chinese remainder theorem is a very important result because it lets you do a lot of things. In particular, it lets you look, when you have many different modulo data, it lets you piece it together, and also doesn't get the opposite. So we'll look at all of that next time. So this is kind of a peek into the Chinese remainder theorem, but let's see what I have for now. Using basic modular arithmetic, I got that n is congruent to 4 mod 5 and that n is congruent to 0 mod 6. What does n congruent to 0 mod 6 mean? That 6 divides n. So n is equal to 6k. I can say that easily, right? I'll plug that in there. So 6k, I want to know something about k now, right? Think of it as like layers of data that I'm stacking on top of each other. N is equal to 6k using this from the second equation. I'll plug this back into the first equation to get some data about k. And in the end, I'll have all the data I can possibly get about this. I don't lose anything in the process, right? So 6k is congruent to 4 mod 5, but 6 mod 5 is just 1. So I have k congruent to 4 mod 5. So n is equal to 6k, where k is congruent to 4 mod 5, right? I can write this in a nice succinct way as, what is this? This is just a fancy way of saying k is some 5l plus 4, or some integer l. Plug that back in. I get n is equal to 6 into 5l plus 4, or 30l plus 24. This is actually a Chinese remainder theorem calculation, but we'll get into that in the next class. So this tells me that n must be of the form 24 plus 30l, or n is congruent to 24 mod 30. I've gotten a much more specific piece of data. If you look into it, this implies both of these. So I'll leave that as an exercise to you. This is a combined piece of data. It loses nothing. It's an equivalent statement. The data of these two statements, same as the data of this statement. I'll leave that to you. Next time I'll pick it up properly. So n is congruent to 24 mod 30. You might say, okay, that doesn't finish the problem. It only gives me part of the data. But look at the equation. What we can now do is bound, right? We have some data about n in the modular sense. Now we can say from here that clearly n is greater than 133, right? Why? 133 is already on the left hand side. So n to the 5 is 133 to the 5 plus other stuff. Right? So n obviously has to be more than 133. So n is more than 133 and n is congruent to 24 mod 30. This kind of gives me only a few options. So n is either, so you can check this, is either going to be 144, that's the first thing, that's the first number, more than 133, it's congruent to 24 mod 30, right? Either 144, the next number that satisfies it is going to be 174, right? Plus 30, and so on. The only thing is, all of these numbers are too large. So that's an argument I want you to figure out on your own. The point is that we used a lower bound to get to the n greater than 133 thing. Now get an upper bound on n. See that essentially, you can combine these two terms, not very hard, to get that n to the 5 is less than 3 times 133 to the 5, right? So in particular, n by 133 is less than the fifth root of 3. But and you can see that any number more than or equal to 174 is too large to satisfy that. I kind of give you a map to do that. In particular, n to the 5 is, you can show it's not much work, that n to the 5 is less than 3 times 133 to the 5. In particular, n by 133 to the 5 is less than 3, or n by 133 is less than 3 to the 1 by 5. It's not too hard to show using some basic numeric inequality, no fancy algebraic stuff, basic number multiplication, that any number greater than equal to 174 is too large for this to happen. There's an upper bound on n, right? So the idea is that 174 or anything more than 174 is too large for this upper bound to hold, right? That's the idea. And so that means that n must be equal to 144, which is the answer. So you already know what the next content of the next class is going to be. We'll look at the Chinese remainder theorem. And I hope today you have got some ideas about how these systems work. We'll also look at modular inverses next time. So really it'll be like a big step in modular arithmetic. That'll be all the fundamentals. There's more stuff you can do, of course, but stuff we've seen till now and the stuff we'll cover next time will really finish a basic fundamental understanding of how we approach number theory. And I hope you enjoyed watching this video. Thank you very much. Bye-bye.